Hello, student. Welcome to this chapter of Ferroelectrics. And today I am going to discuss this ionic displacement and the behavior of barium titanate above the Curie temperature. Here, we'll show that in case the dielectric constant of a material is large compared with unity, a Curie-Weiss law may be obtained which is solely due to electronic and ionic displacements. So this is related to uh, the applicability of Curie-Weiss law to the ferroelectric materials. And actually, this Curie-Weiss law comes for the originally it is derived for the ferromagnetic materials, and that idea or that theory is applied to this material also. Uh, so for the sake of argument, let us assume that for a particle, for a particular non-dipolar solid, the Clausius-Mossetti relation can be written as epsilon minus 1 divided by epsilon plus 2 is equal to 4 by 3 into n alpha, that is equal to beta n. So this Clausius-Mossetti expression is originally derived for the dielectric materials in general. Since ferroelectrics are also the class of a class of dielectric materials, we can use or we can apply the Clausius-Mossetti relation for this ferroelectric material also. So this is the Clausius-Mossetti relation uh, written in its form. So in this expression, this n, capital N, represents the number of unit cells per centimeter cube, and this alpha, represents the total polarizability per unit cell. So the capital N represents how many number of unit cells are there per centimeter cube, and this alpha represents the total polarizability per unit cell. So polarizability means how much of polarization you can create in the material per unit applied field. So in this case, the applied field is the electrical field. So per unit applied electrical field, how much of polarization is produced in the material is called as the polarizability. It is assumed that the alpha is independent of temperature. Alpha will assume actually this also depends on temperature, but here we assume that alpha is independent of temperature. As long as epsilon is of the order of 10 or smaller, any changes any changes in n resulting from the thermal expansion do not affect the value of epsilon to any great extent. So the meaning of this is that when this epsilon is of the order of 10 or smaller, any changes in n means the number of unit cells per centimeter cube, which is not going to affect. Actually, it is changing due to the thermal expansion. When there is a thermal expansion, because there will be changes in the dimensions of the unit cell, then the number of unit cells per centimeter cube will be definitely going to change. But this n, capital N, is a very huge number. Since it is very a huge number as compared to this epsilon, that is a constant. So any changes in this n value will not affect greatly uh, the epsilon value. On the other hand, if epsilon is very very greater than 1, the LHS of equation 1 approaches unity. So this equation is that this is the equation 1, which is the Clausius-Massetti relation. Uh, so on the other hand, if epsilon is very very greater than 1, the LHS of equation 1 approaches unity, and it is seen from the figure that small variations in beta n may lead to large changes in the dielectric constant. So here we have plot a graph of this quantity epsilon minus 1 divided by epsilon plus 2 as a function of log epsilon to the base 10. So this quantity depends upon the value of beta n. So a small changes in beta n leads to very large changes in this quantity. You can see the graph is an exponential graph, and when the epsilon is a very very bigger value, this quantity uh, reaches to an unity. You can see here. So at larger values of epsilon or the dielectric constant, this quantity goes unity. It is very clear in the diagram. So in order to determine the temperature coefficient of this epsilon dielectric constant, we differentiate equation 1 with respect to T. So the LHS of equation T is this one, epsilon minus 1 divided by epsilon plus 2, which is in the U by V form. So you have to use the U by V form and differentiate that equation. So this is U into differentiation of V, that is epsilon minus 1, and minus epsilon minus 1 into differentiation of U. D by dt is again it is d by dt divided by u square. That is equal to beta into n. N I have differentiated, that is dn by dt. So this d by dt is common here. You take out of this bracket. And inside the bracket is epsilon plus 2 minus epsilon plus 1 divided by epsilon plus 2 whole square, and the epsilon get cancelled, and on RHS side this quantity is there. And now on the LHS side we left with 2 plus 1 is 3, 3 divided by epsilon plus 2 whole square into this quantity, that is d by dt is equal to beta into dn by dt. From equation 1, the value of beta is given by, because it is epsilon minus 1 divided by epsilon plus 2 is equal to beta into n is there, equation 1. So from that equation 1 you can get the value of this beta, which is 1 by n into epsilon minus 1 divided by epsilon plus 2, and you substitute this into equation 2. So the equation 2 becomes 3 divided by epsilon plus 2 whole square into d by dt is equal to, here I have substituted the value of beta, that is 1 by n into epsilon minus 1 divided by epsilon plus 2 into dn by dt. So now you can cancel 1 epsilon plus 2 whole square and 1 here. You are left with 3 divided by epsilon plus 2 into epsilon minus 1 into d by dt is equal to 1 by n into dn by dt. Let this is the equation 3. So the quantity 1 by n into dn by dt indicates the variation of the number of unit cells per centimeter cube in xyz axis. Hence it represents the thermal expansion. So as I told, this is a temperature dependent quantity, and if the temperature is changing, this parameter is also changing. So This is indicating actually the thermal expansion. So the thermal expansion is written as 1 by n dn by dt is equal to minus 3 into lambda, where this lambda is the linear coefficient of expansion, where this lambda is called as the linear coefficient of expansion of the solid. So here negative sign comes because of the fact that if this quantity is increasing, this lambda is decreasing. And the 3 comes due to the fact that this thermal expansion is an additive phenomenon. So what is the expansion along x, y, z axis? So in order to count that, 3 is multiplied here. From equations 3 and 4, both are representing 1 by n into dn by dt. So equation 3 is here and equation 4 is here. Here it is RHS, it is LHS, both are same. So we can equate equations 3 and 4. It gives 3 divided by epsilon plus 2 into epsilon minus 1 into d by dt is equal to minus 3 lambda. In the present case, epsilon is very, very greater than 1. Hence, 2 and 1 in the denominator of the above equation can be neglected. Here 2 and here 1 are there. They can be neglected as this epsilon is very, very greater than 1. Hence, we have 3 divided by epsilon square into du by dt is equal to this side, it is minus 3 into lambda. And you cancel this 3 on both sides, and you are left with d by epsilon square, d epsilon by epsilon square is equal to minus lambda into dt. So now you integrate this equation. Integration of this quantity is equal to minus integration of lambda into dt, or this is integrated, it is minus 1 by epsilon is equal to minus lambda into integration of dt is t plus c. Here this lambda is a thermal expansion coefficient, it is constant. So where the c is constant of integration in this equation 5. So or you rewrite that equation, here negative sign is there, you multiply the equation 5 with a negative sign, it becomes 1 by epsilon is equal to lambda t minus c. And now you invert this equation, so it becomes epsilon is equal to 1 divided by lambda t minus c, or epsilon is equal to 1 divided by, from these two terms you take lambda outside, it becomes t minus c by lambda. So lastly I will write this equation as epsilon is equal to 1 by lambda. This lambda I will take into the numerator, so it is written as 1 by lambda divided by t minus theta, where theta is equal to c by lambda. This quantity I represented as a theta and is called as the Curie temperature of the material. And when you look at this equation 6, it is very clear that this equation is of the form Curie-Weiss law, which is derived for the ferromagnetic materials, where it is given by psi is equal to c divided by t minus theta for the ferromagnetic material, where psi is the susceptibility of the ferromagnetic material and c is a Curie constant and t minus theta. So equation 6, we are referring equation 6 as the Curie-Weiss law for the ferroelectric materials. Next, we'll see what are the theories of spontaneous polarization of the barium titanate. So many researchers believe that the spontaneous polarization in barium titanate is due to displacement of Ti4 plus ions. So for based on this fact, For an experimentally observed spontaneous polarization of 50,000 ESU for barium titanate, the displacement required for such an polarization would be 4 NED is equal to 50,000 from theory. Just I am calculating here, where N is the number of dipoles present per unit volume, and E is the electronic charge, and D is the distance. So you calculate D here. This comes out to be 0.15 into 10 power minus 8 centimeter. So that means for this much of spontaneous polarization produced spontaneously, and which is measured experimentally, the amount of displacement required would be this much. That means here we have assumed that the spontaneous polarization is because of the displacement of these titanium ions. So as per this calculation, titanium ions should displace this much towards the oxygen ions. But when you look at this value, it seems to be not correct because it is a very higher value. Actually, the required displacement would be less than this because it is of the order of 10 to the power minus 8 centimeter, and the atomic sizes are itself tend to in terms of angstroms. So this comes out to be a bigger value, and hence this is not true. And the results are based on Lorentz relation. Again, this Lorentz relation is for dielectrics, show that the titanium 4 plus displacement would be less than 38% of the total polarization. So based on this Lorentz relation, it is shown that the displacement of titanium 4 plus ions is not solely responsible for the spontaneous polarization produced in the barium titanate. Only some 38% of the contribution will be from this titanium 4 plus ions and their displacements. So as per the theory developed by Mason and Matthias, titanium 4 plus ions have six stable positions where they have slightly displaced towards oxygen ions, which are present at the middle of each phase. So, according to this theory developed by Mason and Matthias, titanium 4 plus ions have six stable positions where they have slightly displaced towards oxygen ions. So in the unit cell of this barium titanate, the oxygen atoms are present at the middle of each phase, but the titanium ions are present at the corners of the corner unit cell. So what happens? These titanium ions gets displaced towards the oxygen ions. So this gives the six stable states, as there are six oxygen atoms in the unit cell. Hmm. So this displacement is solely is responsible for the spontaneous polarization of the barium titanate. So according to this Mason and Matthias, only the displacement of the titanium ions is solely responsible for the spontaneous polarization produced in the barium titanate. Another theory is based on solely on electronic and ionic displacements. We have seen that the Lorentz field E is equal to gamma p, where gamma is equal to 4 by 3, holds only when all atoms are surrounded cubically by others. So for this internal field theory, it requires that all all atoms should be surrounded cubically by others. So it is a, as you know, it is a cubic structure. The structure of the unit cell is a cubic one, and this is the case for barium 2 plus and Tr4 plus ions, but not for the oxygen ions. So that means only barium ions and titanium ions should be surrounded cubically by others. Hmm? But but the oxygen ions need not be surrounded by the oxygen ions in the barium titanium structure. That means a barium atom or barium ions should be cubically surrounded by barium ions, and titanium ions should be cubically surrounded by the titanium ions. That is the meaning. Calculations of the internal field indicate that in the perovskite structure there exists a strong coupling between the Ti4 plus and O2 minus ions, leading to the internal field constant about 8 times as large as is the usual value 4 by 3 factor. Thus, the internal field at the positions of the Ti4 plus ions is very strong, and this combined with the high charge and small restoring force of the Ti4 plus ion would lead to the conclusion that the perovskite structure is particularly favorable for ferroelectricity to occur. So in this calculation or in this model, the one predicts that uh, there is a strong coupling between the titanium and oxygen ions, and this structure called as the perovskite structure is in such a way that uh, it, it produces a very strong internal field, uh, and as we have studied already, this strong internal field is responsible for the spontaneous polarization produced in the ferroelectricity. ferroelectricity. So that is why we can expect here is that the presence of this perovskite structure in the ferroelectric material is could be the required condition for that material to exhibit the ferroelectricity. So this is about some theories of barium titanate spontaneous polarization, regarding spontaneous polarization. And here we'll move to the another point that is called as the ferroelectric domains. So a domain is defined as a region within which the direction of spontaneous polarization is constant, and the region which separates two domains is called the domain wall. So just like the ferromagnetic domains, here we come across the ferroelectric domains, and the definition of domain is same. It is a small region where either the spontaneous polarization or the in case of ferroelectric materials, or the spontaneous magnetization in case of ferromagnetic materials is constant and which is in one direction, makes the domains. And actually these domains are created to reduce the total energy of the material, because as a nature rule every material or every system wants to be in a state of least energy. So for that For that, the ferroelectric or ferromagnetic materials, what they do, they develop the smaller regions inside their surface, and where the polarization or the magnetization are having one direction. So this kind of small regions are called as the domains. Next, when the volume of domains in opposite sense are equal, the crystal as a whole will appear to be unpolarized. So let us think that you have two domains, and their volumes are equal, and but they have the opposite sense. That means they are the polarization in those domains is exactly opposite to each other. Then what happens? The net dipole moment of one dipole will get cancelled by the net dipole moment of the other domain. So because of that reason, we say that the crystal is an unpolarized one. The total dipole moment of a crystal is therefore changed by the movement of the walls between the domains or by nucleation of new domains. So the total dipole moment of the crystal changes depending upon how many number of dipoles these domains are there, and the domain number is changing because of the wall movements or because of the nucleation of new domains. So charges are produced on the surface of perpendicular on the surface is perpendicular to the direction of polarization. The electric field is therefore not zero. That means over the surface of the ferroelectric material, charges are collected or developed. So these collected charges create some electric field. This electric field is not zero, and there is a depolarizing field due to the surface charge. This developed field is called as a depolarizing field. The electrostatic energy due to the depolarizing field may be written as UE is equal to 1 over 3 gamma Ps square into Vs. So this is the electrostatic energy due to the depolarizing field, where Vs is the volume of the sample and gamma is the depolarizing factor, and which depends on the shape of the sample. If a sample is divided into a number of domains, each showing uniform saturation polarization and being surrounded by domains of opposite polarity, the depolarizing field will be reduced, which is a reason for the formation of domains. So that means in order to decrease the energy of the system around one domain, other domains are surrounded, and the polarization in surrounded domains is in such a way that the net dipole moment is going to be at a minimum level. So that decreases the energy of the system and thereby decreasing the depolarizing field. So next, adjacent domains are separated by walls uh, in which uh, in which polarization changes gradually from plus PS to minus PS. PS means saturation polarization. So when you are moving from one domain to next adjacent domain, you will have to cross the wall. When you cross the wall, what happens? So wall is having a certain thickness, and when you are crossing the wall, what is found is that this saturation polarization gradually changes its value or direction, whereas the strain changes gradually from plus ES to minus ES. So strain is also produced there. So when you are crossing the one domain, to the other domain, the strain produced there also changes its direction and value. The electrostatic energy UE decreases decreases with increase in the number of domains because of the decrease in depolarizing field. So as the number of domains increases, the depolarizing field decreases because the polarization in all these domains are oriented in randomly position, so that reduces the depolarizing field. Thus, the splitting up into domains continues until the total energy is a minimum. So that is why the bigger domains split up into the smaller ones, and they arrange in a random way so that the total energy of the system is a minimum. That is why when you look at the developments or the growth and decay of these domains, the one point is clear that they will adjust their sizes and number in such a way that the total energy of the system is a minimum. Next, the energy per square meter stored in a wall consists of two parts. So this is referring to only the wall. The energy the energy per square meter stored in a wall consists of two parts. One is the first part is the dipole part due to change in polarization from plus B to minus from plus PS to minus PS in the wall, and the other part is the elastic part due to change in stress from plus ES to minus ES. So the energy per square meter in the wall is changing because of these 2 points. One contribution is from dipoles, as the dipole part, as the polarization is changing from plus PS to minus PS, and another part is because of the fact that the stress is also changing from plus ES to minus ES. So these two factors decides the wall energy. In ferroelectric substances, the wall thickness is of the order of a few lattice spacings, and the wall energy is about 10 to the power minus 2 joules per meter square. So the thickness of the wall is about few lattice spacings, or lattice constant. You know, the lattice constant means it is the it is the distance between two successive atoms in the lattice. So that distance is generally of the order of 1 angstroms, or it will be in terms of angstroms. And you can imagine uh, that means it is very clear that the thickness of these domain walls is some few angstroms. We can say that it is some few angstroms, and the wall energy is about 10 power minus 2 joules per meter square. So if the directions of polarization in the two sides of the wall differ by 180-degree, they are called as 180-degree walls. So here you can see in this diagram, these are the two domains separated by this wall, and here the direction of polarization in this domain is upward, whereas the direction of polarization in this domain is downward. The angle between the direction of polarization of these two domains is 180-degree, and hence it is called as a 180-degree wall. This wall there is called as a 180-degree wall. 180-degree domain walls are found in rock salt or the potassium dihydrogen phosphate. If the domain walls of the adjacent domain are making an angle of 90 degree. They are called as the 90-degree walls as shown in the figure, and this kind of domains are found in barium titanate. So you can look at this diagram. This is one domain, this is another domain. The direction of polarization in this domain is in this way. The direction of polarization in this domain is in this way. So the angle between the direction of polarization of this domain and this domain is now 90 degree. Because of this reason, this wall is called as a 90-degree wall, and this kind of 90-degree wall domains are found in case of the barium titanate, even though it possesses three phases. So this is all about ferroelectric domains and dipole theory, and about the Curie Weiss law for the uh, ferroelectric materials. Thanks for watching.